is Flash Isaac, and I'm a teacher from the future. We shall be dealing with fluids at rest and fluids in motion. Fluids at rest and fluids in motion. If you are going further in your studies of physics and mathematics, you will encounter a topic called mechanics. Mechanics is simply a branch of physics or of chemistry or of engineering that studies the relationship between force, matter, and motion. Mechanics study motion in objects and in fluids. Motion is divided into mechanics is divided into statics and dynamics. Statics studies objects at rest, while dynamic studies objects in motion. Mechanics study the relationship between force, motion, and matter. Force is agent that changes the state of rest or uniform motion of a body. Forces cause objects to move, to stop moving, or to change direction. While matter is anything that has mass and occupies space. Matter can exist as solid, as liquids, and as gases. When you wish to describe matter in liquid and gaseous state with just one word, you call them fluids. So, liquids and gases are referred to as fluids. Motion, on the other hand, is change in position of objects with respect to time. And the reason for motion is force. Fluids can be at rest and they can be in motion. When you are studying fluids at rest, you are simply studying fluid statics or hydrostatics. When you are studying fluid in motion, you are simply studying fluids dynamics. So, when is a fluid or when are fluids said to be at rest and when are they said to be in motion? Before we go into that, let's look at the forces that act on substances. Let's see the forces acting on both solids and even on liquids. The first we shall look at is tension. Tension is a force on stretched ropes and springs. When you put two objects apart, like rope and springs, and they say, find the tension in the rope or find the tension in the spring, they are simply saying, find the force or the force developed. The second force acting on substances is thrust. Thrust or thrusts are forces exerted when two parts or parts of a body or parts of bodies are brought together. Like the force between two of your legs, they are thrust, trying to hold your body together. The force in the legs of tables, that is thrust. As you are pushing wheelbarrow, you see the force trying to bring two parts together. That is thrust. Now, for aeroplane, there are four forces acting. The first force is the drag force. Drag. The drag force is the force trying to push the aeroplane backward. Do not move. Do not move. Then we have the thrust. Thrust is the power of the engine trying to push all the parts together and make the aeroplane to move. For an aeroplane to move forward, the thrust must be greater than the drag force. And there is a force like this, which is the lift force, and there is weight. Lift is the force trying to pull the aeroplane or the object upward, and weight is the force pushing the object down. Anywhere in physics or in mathematics, the weight of objects always adds downwards. And there is a force equal and opposite the weight, which is called normal reaction. So long you are not moving down or going up, standing like this, your weight is the same thing as your normal reaction. Now, let's see another force acting on substances. Upthrust. Upthrust is a force experienced by objects immersed in a fluid. Once you put an object in a fluid, either gas or liquids, the force experienced by this object in the fluid is referred to as upthrust. When an object is partially or totally soaked or pushed inside a fluid, that force that the object experienced is what we refer to as what? Upthrust. Now, the upthrust in water, in liquid, is greater than the upthrust experienced for an object floating in the air. Why? Because the density of liquid or of water generally is more than the density of fluid. And upthrust is equals rho GV. Now look at this. Upthrust is directly proportional to pressure. As pressure increases, upthrust will increase. As upthrust increases, pressure will increase. 2. Upthrust increases with depth, just like pressure. In the previous episode, we discussed pressure, and we said that pressure increases with depth. Also, upthrust increases with depth. The deeper you go, the more the upthrust. 3. Upthrust does not depend on temperature. No. The force experienced when an object, a body, is immersed in a fluid is independent on temperature, but it depends on the height. And upthrust is density, gravity times volume. Now let's see the fourth force acting on substances. Density. Density is mass over volume. The mass of a substance divided by the volume that substance is occupying is referred to as density. Look at oil. Look at engine oil. Look at petrol. You will see that engine oil is very, very thick, while petrol is so light. So if you compare the mass over volume of the engine oil, it is more than the mass over volume of the petrol. Therefore, engine oil is so dense. It has more of that substance per a particular area or per a particular volume. There is what we call relative density. Relative density of a substance is the density of that substance over the density of equal volume of water. That is relative density of any substance. So, the major forces acting on substances that you should know are tension, thrust, upthrust, and density. Other fluids at rest, you should know some of the applications of density or relative density. Remember, density is mass over volume, while relative density is the mass of a substance or of an object compared to equal mass or equal volume of water. Talking about liquids at rest, you should know pressure, density, surface tension, flotation law, Archimedes principle, and Pascal's principle. Pascal's principle was explained under pressure in the previous episode. For incompressible liquids, when you apply pressure on the water, it is evenly distributed around. So, pressure is force per unit area, which we also dealt with in the previous episode. Now, we are looking at density, which we said mass over volume. And density finds application in floating of ship. When water solidifies, what happens? When ice melts, what happens? And why does ice float in water? Why does ship float in water? Because ship is so massive. Why don't the ship sink? This is where Archimedes' principle and the law of flotation comes in. Remember, I told you that when you immerse an object in a fluid, the push you get is upthrust. Like, let's say we have a ball. Now, if you try it, a big basin of water or a river, if you try to force the ball inside the water, you notice that there's another force pushing it up. That force may even throw you away. That force you experience, the reverse force, is upthrust. So, Archimedes' principle states that the upthrust experienced when you immerse fluids in water is equals the weight of that object. So, the more the weight you have, the more the upthrust, the more the push you get from fluids or from liquids. And the law of flotation states that for objects to float in water or in liquid, the weight of the object should be equals the weight of the liquid displaced. Now, if this is water, this is surface of the water, and this is ship. This ship has its own weight. This water has its own weight or its own mass. Let's use mass now. As this ship enters the water, the mass of the water this ship is displacing should be more than the mass of the ship. If the mass of water is greater than the mass of the ship, or the mass of the water the ship displaces is more than the mass of the ship, then the ship is able to float in water. Because the water isn't really having any problem. Let's say there is a particular mass here, 100 kg, right? Then the ship comes on top and displaces around 90 kg. So the water still feels its mass, even extra. It will not notice the weight of the ship. So that is the reason object floats. And generally, for objects to float in water, the density of that object should be lesser than the density of water. Water needs to be denser than that object. And what will make the density of that object lesser than the density of water? It is simply the volume of water displaced should be more than the volume of the mass of that object. So, why does ice float in water? This is because volume of water is less and the density of water is greater than that of the ice. Now look at something. Ships float because the mass of water is greater than the mass of the ship. The volume of water displaced is more than the volume of the mass of the ship. Density is mass over volume. Now, when water solidifies, the volume increases and the density reduces. So, the density of water is more than the density of ice. And the volume occupied by ice is greater than the volume of water. So, the volume of water is less. And what happens when ice melts? When ice melts, the volume drops. There is a drop in volume and an increase in density. You should know that density is inversely proportional to volume. As volume increase, density will drop. As volume drop, density will increase. So, the law of flotation states that for objects to float, the density of the object should be equal to the density of the liquid, or the weight of the object should be equal to the weight of the liquid. And Archimedes' principle states that the upthrust experienced by a body is equals to weight. How about surface tension? If you look at water or liquids generally, you observe the surface very well. You will see that it seems the surface is covered by an elastic skin. And have you ever wondered why is it that when you put a dry needle on top of water, the needle will float, it will not sink? When water is just liquid, why do you think that certain insects with needle-like leg, they will be walking on top of water? In fact, if you are asked why things walk on water and you look at the things that they are very tiny, the explanation should be surface tension. Water acts as if something is covering its elastic skin. All these phenomena I explained are due to surface tension, a phenomenon that makes water behave as if it is covered by an elastic skin. And by definition, or if you choose to use big grammar, surface tension is force acting tangentially per unit length, and it makes surface behave like elastic skin. Surface tension can be explained by molecular or kinetic theory. Application of surface tension are formation of soap bubbles, those bubbles of soap while you are washing, that is as a result of surface tension. Now, you see the shape of liquid drops, the way they are thick, they are as if covered, they have certain shape, meniscus. That is application of surface tension. And capillarity is an application of surface tension. Look at this. If you have a narrow capillary tube like this, or you have a basin, or even in soil, the rise of water in soil, or the rise of water in a narrow capillary tube is as a result of surface. What is the reason for capillarity? It is simply adhesion and cohesion. Adhesion is the force of attraction between molecules of different substances. If you have glass and you have water, the force between the water and the glass, since they are different substances, is referred to as adhesion. Cohesion is the force of attraction between molecules of the same substance. If you have water and water, the force acting between water itself is cohesion. Look at this. The adhesion of water is greater than cohesion. The force of attraction between water and glass or water and object is so big, it is bigger than the force between water. So water will want to leave itself and jump to glass. Since the force or cohesion of water is not big, so this water molecule, you see glass, you are jumping to meet glass. You are leaving yourself, jumping to meet glass, because you are more attracted to glass than even yourself. So you jump to meet glass. As such, there is rise in level of liquids. Now, for mercury, the cohesion of mercury is bigger than the adhesion. Mercury, they love themselves so much. So the force that they are using to cuddle is bigger than the one for surface. So they don't even care about the water, glass surface or any surface they are in. They love themselves. Glass, no. As such, mercury will not wet glass because their cohesion is very strong. So, rise in water is due to adhesion. Mercury forms convex meniscus. If you put mercury in glass, you see something like this. This is how the water will be. If you put water in glass, this is how water will be. So water forms concave. Mercury forms convex meniscus. And there is something called contact angle. Contact angle is the angle between the normal of the liquid surface and the normal of the solid in mass. The contact angle is the angle between the liquid surface and the normal of the solid. For substances that wet glass, or for substances that have strong adhesion, the contact angle will be zero. Like water should have zero contact angle. For substances that have strong cohesion, like molecules that have strong cohesive force, the contact angle will be around 180 degrees. 180 is the maximum. So for a perfectly cohesive substance, contact angle is 180 degrees. Mercury and glass, the contact angle between them is 140 degrees. And to reduce surface tension, you can add camphor, you can add alkanol or alcohol, you can add kerosene, you can add camphor, you can add detergent, or you add spirit. All these guys will reduce surface tension. But if you want to increase surface tension, you must add oil, you must add grease, and you must add wax. Ladies and gentlemen, let's see one or two under liquids in motion. Fluids can also move, or we can study the movement of fluids. When it comes to fluids in motion, the three things you should know are flow rate, viscosity, and diffusion. These are the big boys that need to be studied under fluids in motion. Flow rate can be volume flow rate, and it can be mass flow rate. Volume flow rate is simply the volume of liquid flowing over time. If you are given a fluid, how much or what volume is able to float or change position or displace with time, that is volume flow rate. Then mass flow rate is mass of the fluid over time. If volume flow rate is volume over time, remember, volume is length times breadth times height, and length times breadth is area. So area times height is volume. Therefore, volume flow rate is area times height divided by time. And height speaks of distance, which means instead of height, you can say that volume flow rate is area times distance divided by time. Since we are dealing with fluid in motion, your knowledge of motion, Newton's law of equations of motion should come to place. In motion, displacement over time is simply velocity. So d over time is equals av, which means depending on the parameters you are given, you can find volume flow rate by saying volume over time, or area times height over time, or area times d over time, or av. V over t, ah over t, ad over t, or av. Mass flow rate is mass over time. Remember, density is mass over volume. Therefore, mass is density times volume, which implies that if mass flow rate is mass over time, it is also density times volume over time, rho v over t. If you are calculating force exerted, it is rho a hv over t, or rho a v squared. Volume flow rate is av, mass flow rate is density times av, force exerted is density times av squared. When it comes to calculations, we shall see all that. What is viscosity? Viscosity is the resistance of fluid to flow or change in shape. We know that one of the differences, dichotomy, similarity, disparity between solids and liquids is that liquids take the shape of the container. If you pour water inside a container, it will immediately take the shape. How about grease, engine oil, all these thick substances? If you pour them in container, they will eventually take the shape of the container, but they will do gra. Like you see honey, as you are pouring, it will take time for them to spread and take the shape of the container. Some may not even want to take the shape of the container. At the top, you will still see them. This is the container. Here they've spread, but here they can even still be like this to stand. They don't want to spread. Pride wants to kill them. So some liquids don't flow easily. Honey, engine oil, all these guys, they don't really flow easily or change shape easily. So the resistance offered by shear stress to flow of this fluid is called viscosity. Engine oil, grease, and those guys, they are very viscous. Meanwhile, water, petrol are not so viscous. Now, listen. Viscosity depends on nature of surface, like roughness or smoothness. Just like friction, viscosity depends on the nature of surface. You may be asked, which of the following is a similarity between viscosity and friction? It is simply the nature of the surface they depend on. Just like friction is force that opposes motion, viscosity is also resistance to motion, and it depends on the nature of the surface. However, viscosity depends on surface area and relative velocity. This is a difference between friction and viscosity. Friction does not depend on area and relative velocity. However, viscosity depends on area and it depends on relative velocity. Objects in viscous fluid flow slowly with time and then with constant maximum velocity. Objects with viscous fluid, with time, they will first of all flow small. Later, they will flow with a constant maximum velocity. That constant maximum velocity is referred to as terminal velocity. So terminal velocity is when viscous objects flow with constant maximum velocity. And when does this happen? Constant maximum velocity happens, or terminal velocity happens, when force acting is equals 0. When force acting is 0, then the object has attained terminal velocity. And for liquids generally, as temperature increases, the viscosity will reduce. For gases generally, or for most gases, as temperature increases, viscosity will increase. Now, for lubricating oils, their viscosity is not affected by temperature. And these are referred to as viscostatic liquid. Viscostatic. When a liquid is viscostatic, it means that its viscosity is not affected by temperature. And there are laws of viscosity or fluid friction generally. You can refer to viscosity as friction in fluids, while friction in solids are referred to as friction generally. The two laws of viscosity are Newton's law and Stokes' law. You may be surprised, what is Newton doing here again? In fact, when it comes to viscosity, Newton has two laws here. The first one is the law of stress law. It states that shear stress is proportional to velocity gradient. This is shear stress, this is velocity gradient. So, as stress increases, the velocity gradient will increase. As shear stress reduces, the velocity gradient will reduce. And what is shear stress? Stress is force over area. What is velocity gradient? Velocity gradient is velocity divided by length. So, if you are asked to look for dimension of velocity gradient, you simply say that velocity gradient is velocity over length, then velocity, you look for the dimension of velocity, distance over time, L over T. So L over T over L, something like that. And since this is force over area is proportional to V over L, force will therefore be equals this guy, which is viscosity times area times V over L. Once you cross multiply and you introduce an equality, a constant. Changing proportionality to equality, you introduce a constant, which is the viscosity. So viscosity is therefore force over area, volume over length. Now, the second law of viscosity by Newton is the drag or resistance law. it states that the drag is proportional to density, area, and volume spared. While Stokes' law states that the drag on a sphere for spherical surfaces is equals 3 pi mdv or 6 pi m rho v. Diffusion. Diffusion is simply mixing of gases, mixing of molecules of substances, or movement of particles or substances or molecules from region of high concentration to medium of lower concentration until it is evenly distributed. Diffusion is inversely proportional to mass. The more the mass, the lesser the rate of diffusion. The lesser the mass, the more the rate of diffusion. And diffusion is directly proportional to temperature. As temperature increases, rate of diffusion increases. As temperature drops, rate of diffusion will also drop. And Graham's law of diffusion states that the rate of diffusion is inversely proportional to the square root of density, and provided the temperature and pressure are kept constant. For different objects, let's say two objects, the rate of diffusion of one over the rate of diffusion of the other one is equals the density of the other one divided by the density of the first one. R1 over R2 is equals D2 over D1. With this, we've covered fluids at rest, fluids in motion, and forces acting on substances. Let's look at hot cake questions under fluids at rest and fluids in motion. Why you shouldn't fail to meditate on this formula. In case the need arises, you should know what to do. A body of mass 2.5 kg, M is equals 2.5 kg, and density 5,000 kilogram per meter cube, rho per meter cube, is fully immersed in water. The upthrust by the body is upthrust is equals question. Now, I told you that from Archimedes' principle, the upthrust by a body is equals the weight of that body, which means the upthrust will simply be equals. Let's look at which formula will work. Upthrust is equals weight. Upthrust is equals mass times gravity, since weight is mg. Upthrust is density times volume times gravity. Why? Mass, density is mass over volume. So volume, mass is volume times density. So volume times density times g is also upthrust. And upthrust is also the density of water times the mass of the substance given, or the mass of solid, times gravity all over density of solid. Now, we have, what do we have? Mass of the body, and we have density of the body. In this type of question, you don't expect anyone to give you the density of water. The density of water is constant. Density of water is 1,000 kilogram per meter cube. So, if you are given questions like this and you are not given density of water, in fact, write the density of water out first for any question that has to do with fluid in motion. From here, we have the density of water, we have the density of the substance or solid, and we have the mass of the substance. So upthrust will simply be this formula: density of water times mass of the substance times g all over density of the substance. And what should this give you? This should give you 1,000 times 2.5 times 10 all over 5,000. This should be, this cancels this, 10 divided by 5 is 2. 5 divided by 5 is 1. So we are left with 2.5 times 2, and that is equals 5. So 5 is the upthrust. Upthrust is the same thing as weight or force. So it is 5 Newton. Option A is the correct option. The density of a certain oil on frying becomes rho on frying becomes 0.4 kilogram per meter cube, with a volume on frying is 20 meter cube. What will be its initial volume when its initial density is 0.8 kilogram per meter cube? Now, let's say density before frying, let's say B density before frying is 0.8 kilogram per meter cube, and volume before frying is our question. Assuming no loss of oil due to spillage. Look at this. Density is mass over volume. So long there is no loss of what? Oil due to spillage, the mass will remain constant. The mass when frying or the mass during boiling remains constant. During frying and boiling, mass does not change. And if mass does not change, it means that density times volume is equals mass, and mass is constant. So density before frying times volume before frying is equals the mass. Then density after frying times volume after frying is also equals mass, and mass does not change. So rho BF times VBF is equals rho F times VF. All this I am doing, they are just grammar. If you are given the same object and you are comparing volume and density, you simply say that rho 1 V1 is equals rho 2 V2. Simple. This is before frying, that is after frying. Now, before frying, density is 0.8 times volume before frying. This is equals, after frying, the density dropped drastically, that is to 0.4 over times the volume is 20 meter cube. If I am given this type of questions, I doubt if I need to even solve, since density is inversely proportional to volume. As volume increases, density will drop. As density increases, volume will drop. Here, density dropped by half. It means the volume will also drop by half. Density moved from 0.8 to 0.4. That is exactly half. Volume should move from 20 to 10. Simple as AB. But without assumption, V is equals 0.4 times 20 over 0.8. If solved correctly, you should get 10 kilogram per meter cube. What option is even that? Option B is correct. Water and kerosene are drawn respectively into the two limbs of a Hertz apparatus. That is your problem, I don't care. I just know that you're talking about water and kerosene. Anywhere you are drawing them into, it's not my business. The density of water, rho of water, is 1 grams per cm cube. This is the same thing as 1000 kilogram per meter cube. Yes, something like that. Density of water. And the density of kerosene is rho K is equals 0.8 grams per cm cube. Look at this. Since this is in grams, we should work with them under the same unit. No need to use different units. If the height of the water is equals 20, and what is the height of the kerosene? HK is equals question. Ladies and gentlemen, density is inversely proportional to height. Density depends on height. As density increases, height will reduce. As height increases, density will drop. If this is so, it means that D1 H1 is equals D2 H2. Since there is a constant here, what do? Density of water is 1 times height 20 is equals 0.8 times height of kerosene. The height of kerosene will simply be 20 divided by 0.8. This is the same thing as 20 divided by 8 over 10. 0.8 is the same thing as 8 over 10. Once you move this once, you get to the end. So that is 8 over 10. This is the same thing as 20 times 10 over 8. 2 into 8, 4. 2 into 10, 5. 2 into 4, 2. 20 into 2, 10. 5 here, 2 here, 5. 2 here, 1. 5 times 5 is 25. Ladies and gentlemen, you don't need to understand what I did, but if you understand, nice one. 20 divided by 0.8 is 25. So the answer is 25 centimeters. The net downward force on a metal ball falling through a liquid at the terminal velocity is, at terminal velocity, force is 0. I said this earlier. And the rise or fall of a liquid in a narrow tube is because of surface tension. Yes. Look at this. A. Osmotic pressure. B. Friction between the walls of the tube and the liquid. C. Surface tension of the liquid. D. Viscosity of the liquid. Now, surface tension is the reason for rise and fall of liquid in a narrow tube. But the process is referred to as capillarity. The rise and fall is capillarity, but the reason for it is surface tension, like I explained earlier. Thanks for watching. Your one and only teacher from the future. I hope you found this class interesting. Feel free to check out the playlist for more amazing videos, and don't fail to install the Flash Learners application right now for notes, videos and questions to meet all your needs. Subscribe to this channel so you don't miss out any of my sweet videos. See you in the next episode. Don't forget to tell everyone around about the Flash Learners. Bye.